Hope you guys can see me. Here we go. All right, everybody, we're going to be doing the Bowlero problem. This is a really, really cool physics problem. It kind of goes into angular velocity and just like talks about the different kinetic equations and how they relate. So let's get into this real quick. So for the Bowlero problem, we are given a really solid diagram. Okay. So we have David the professor with a bowling ball. There is a meter above the ground, right up here. We then have the delivery right up here. Okay. So we have the delivery, and then we have the ball that's moving. So really, you're going to be looking right over here at the angular velocity. But let's kind of get what we have so far, what we've been given. So the height that we've been given is 1 meter above the ground. We also have the mass of the ball, the bowling ball, which is 5 kilograms, and then we're also given the radius of the ball, which is 0.11 meters. So this is the really good information that we have. Not only that, but we do also have, we have VL1, okay, which is 1 meter per second, but we do not have VL2 or VL3. We have the rotational velocity as well. So this is going to be right over here. So we'll just call this V1 or W1. I forgot the Greek letter term, but this is going to be 0 meters per second or 0 rad. Let's do that. Because you don't have any rotational velocity going on right over here, or angular velocity. But if we go right over here, we have this one. This also is 0 rad. Okay. And we do not have the third one. Now, what else are we given? So we're given some equations, of course. So impulse, which is 2/5, the mass of the ball times the radius of the ball squared. Okay. And then we also have kinetic energy, gravitational energy, and rotational or potential energy. And right over here for kinetic, okay, you're going to have 1/2 times mass times velocity squared. For gravitational, it's going to be mass times gravity times height. So those are the equations right over here. And then with this one, we also have 1/2 I impulse, and then this Greek letter squared. So that's what we've been given right now. But we also are given some charts that we can kind of think about real quick. So like with some energy charts. Let's get some energy charts going. So right over here, let's use a blue marker. So make it a little easier to read. So we have an energy chart, and as we can tell right over here, we're mainly using gravity. Gravity is going to be the one that's pulling down the most energy. This is like the instance that he's like starting to swing the ball down towards the floor. So let's put that right over here. Let's use 5 blocks because we like 5. And then we have the kinetic. That's going to be just a little bit. And then we also have the rotational or the potential. So this is going to be event 1. Then we go to this one. There's no gravitational that we're working on. This is all transferred into kinetic energy. Well, actually, I'm trying to go 4 and then 1 more right over there. So we have that. And then we have the rotational one. So nothing's transferring to rotational, it's just all kinetic energy now. Then we're going to go over here. And we have the gravitational energy. Still not using any of that at this moment. But we are using a lot of kinetic energy still. It's transferring. And then we have the rotational energy, which has 2. So this is what we've been getting so far. So let's see if we can find VL2. So linear velocity 2. Find VL2. So what can we do to find VL2? So we can actually use this equation right over here with these equations. So let's do this one. So we have EG, EG1 plus
Oh, no, I'm going
K1
to
is equal to EK2. What do we know about this? Let's actually get some values down, or some the equations. Replacing the equations.
You know, I would.
So this is what we have so far. And this is actually a pretty easy equation that we can do. So if we go over here, take 2n, put it to both sides, right there, cancel out the n, cancel out the n right over there, cancel out that 2, but this still is going to have 2. So we have 2 times gravity times height plus velocity 1 squared equals, now it's velocity, or the linear velocity 2 squared. So this is actually really, really easy now. So we have 2 times 10, because that's the acceleration of gravity, of course. About gravity, times height, which is actually 1. Plus, so we already know right up here, VL1, or linear velocity 1, is 1, and you know we know 1 squared is 1, so we have 1, and then we have V2 squared. Now we have 21 equal to V2. Get that, V2 equals 21 squared, which is equal to 4.6 meters per second squared. So now we have that. So 4.6 meters per second squared. Look at that handwriting. That is absolutely stunning. Now we're going to move this right over to here. We're going to find linear velocity 3 and rotational velocity 3. Okay? So we're going to find those. So how do you think we're going to find these? Guess what? Let me tell you. We already have these energy bar charts to help us out. So we already have this one. So EK2 is equal to EK3 plus ER3. So this is actually a pretty easy question, right? So we have 1/2 times mass times velocity squared. So it's going to be 2 equal to 1/2 mass. Oh, whoops. My mistake. 1/2 mass times velocity squared as well. So that's going to be V3. We're going to be looking for that one. And then we have plus. Get so many messages right now. It's unbelievable. We also have right over here this equation. 1/2 impulse times the angular velocity, or the rad 3. So we have all this right over here. This is actually pretty easy. So what we can do is we can actually multiply both sides by 2n.
So just as long as there's something.
So we have that.
That's
right?
all that matters.
So we're going to have V2, so linear velocity 2 squared, is equal to, so we can cancel this one out as well. So we have V3 plus, okay, we already have that. Cancel that out, so on and so forth. I times mass. So right over here. So this is what we have so far. But what we need to do is we actually need to use another equation. So let's get this black marker. We go right over to here. You have W equals, or actually, velocity is equal to WR, which is radius. So what we have is angular velocity is equal to velocity divided by the radius of the ball. So we can actually use this really, really quick, and we also know I. Cancel out some things real quick. So we go V2 is equal to V3 plus 2/5 times this equation. So we got the mass of the ball. The radius of the ball squared. Okay, remember this? Okay. We also have this, so we're going to be working off of this right over here. So the third linear velocity squared is all going to be right over here. So this is what we have so far, all divided by n. Actually, kind of simplify it a little bit. So this makes it really, really easy. So first off, we just take out the mass, and then we can take out the radius of the ball as well, because this is squared and this is going to be squared. So what we get right over here is the linear velocity, the third linear velocity, plus 2/7 the linear velocity. It's super easy. So now what we can do is we can get this, make this 7/5, because this is going to be 1. You know, you use your fractions, use that common sense, of course. We have 7/5 times the third linear velocity squared. Now we can finally plug some stuff in, okay? We already know this. So this is going to be 4.6.
Yeah, that's fine.
Times 2.
Yeah, 'cause
We're
that's
actually,
not
no,
the point, right?
We're going to make it a little easier.
You memorizing formulas.
Square root both sides.
About
Okay. So we have now is v, so linear velocity 2 is equal to 7/5 v3. So what we can do is we can actually just plug this in. So we have 4.6 divided by, and what this is going to be is 1.4. 1.4. 1.4. Yeah, no, that is right. Divided by 1.4 is equal to v3. And now I need a calculator. Does anyone have a calculator I could borrow real quick? Por favor.
Oh, speaking of which, did somebody leave a calculator one time?
There was the guy with the dreads. He left.
Caleb's.
Yeah.
Which day?
We're almost there.
Yeah, there's this one, and I've got some simpler ones if you want calculators.
I'll be right back. I need to grab a calculator.
Huh? Yeah.
Okay. So now 4.6 divided by 1.4. You're going to be getting 3.28. Essentially. I think that's right. Here, one sec. 4.6 v2. 4.6.
These are like a couple of like. No, it's not 100.
Oh no. I did that wrong. So we'll just do this real quick. Let me get that other marker. Go like this. Is this still recording? Okay, we're good. So you're gonna have the linear velocity of this is going to be 3.9 meters per second. So we have this now. Meters per second. Sorry, not meters per second squared. We have this one. So 3.9 meters per second. And then we can actually get the angular velocity and do, so we're going to be using V3. So we have that right over here. So we have V3, which is 3.9 meters per second, divided by the radius of the ball. And that's going to be 35.45. 35.45 rad.
I think you put it in the wrong direction.
So, this is what we got so far. 35.45. And here's the question. We need to think about a question. Or we have a question. It's given to us. What is the force of David's arm on the ball? So, let's go to that. Let's use another marker. Got a red one right over here. So, if we go to right over here, we know a few things. So we know the force diagram of this, which is the force of the earth on the ball and the force of David on the ball. Okay. We also know, this is beautiful, is that this is 1 meter. This is also 1 meter. So the length of his arm is going to be 1 meter in this question. So what we know also is we need the centripetal acceleration equation, which is actually velocity squared divided by r. R in this is going to be 1 meter. So super easy. So now what we can do is we can actually use the force diagram, right? So, or the
No, but if I said
summation of
this,
the
then
forces
the 3 videos on like
equals MA. That's what it is.
Why is it 3?
I think that's what it's called.
It's one for
But yeah.
me, one for you.
So, you know, we know
Two-
force,
it can be
forces
two for me,
equal,
two
or
for
the
you.
summation of, or force equals mass times acceleration. So we have right over here
Just send me
is the
this.
summation of forces. So let's do this now.
They
So
want-
first off,
they went today.
we
I
have-
solved the Bowlero problem.
we're trying to look for
So for this problem,
the forces of David on the ball.
first of all,
We have that.
we
Then we have the force of the earth on the ball, which is equal to the centripetal equation
the moment
right over
that you
here,
approach the Bowlero,
or mass times the centripetal equation. So let's go to force of David on the ball. Let's plug this stuff in. So what do we already know about this one? So it's going to be mass times gravity, which is also equal to mass times velocity squared. And we're focusing on delivery, okay? We're focusing on this portion right over here. So super easy. So what we can do is we can just go like this. And this is going to be the linear velocity 2. So that's linear velocity 2. So now let's do some quick maths. Let's actually add this to both sides because we're trying to look for this, right? So mass times gravity. Okay. Mass times gravity plus mass times velocity, linear velocity 2, times r. And now we can start getting to business. So we can go like this, make it super easy. So we have the mass, we just kind of like got that out, okay? So we have gravity, which is 10, plus this right over here. So this is going to be 4.6.
So you can notice that
4.6 squared
the sum of
divided by the length,
energy
which is just 1.
equals to
And then what we can do right over here
so the first equation
is go the mass of the ball, which is 5 kilograms, times this, plus, to get this really quick, 4.6 squared, it's going to be 21, 21.16.
So I know that EG1 would be
Pretty sure that's just meters per second.
times gravity times I.
So now what we can do is go like this. So force of David on the ball
Mass times
equals 5 kilograms plus 31.16 meters per second. And then we can just multiply this. 5 times 31.16 is equal to 155.8 newtons. So this is how we do the Bowlero problem. And let me tell you, that is the best handwriting I think I've ever had. Okay. So we have the force of David on the ball on this section. We found linear velocity 3, angular velocity as well, or 3, angular velocity 3. And then we also found V2, so linear velocity 2. So that's what we have so far, and I hope you enjoyed. Thank you so much.